and we'll go from current slide. Okay, sorry we're a little late getting started, but now that we are going, let's just do a quick review. Last time we got into topic 17, 17.4, and that's where we're picking up tonight. I hope that we'll finish the chapter, the topic, before seven, and if we do, then we're going to do our lab, and if we do that, I'll give you your test. Okay. So, any questions? We might even be able to start topic 18. We'll see if we got time. Any questions? Yes.
I just wanted to change my
Okay, that's fine. That can be done anytime. You don't have to write it down for me, but if you turn in something, I'll give it to you. So you can do that. All right. Ohm's law. Okay. We talked about Georg Ohm. Experiments show that for many materials, including most metals, the resistance remains constant over a wide range of applied voltages and currents. Okay? That statement has been, this statement has become known as Ohm's law. Basically, what previously we said, the voltage is proportional to the current. That's what Ohm recognized for many materials under many circumstances. The voltage is directly proportional to the current. What was that proportionality constant? He called it the resistance. Okay? And Ohm's law is an empirical relationship that is valid only for certain materials. Most materials, true, but only for some. Materials that obey Ohm's law are said to be ohmic materials. Named after Ohm. Everything's named after Ohm because he did so much of this early work with this. So here is an ohmic device. The resistance is constant over a wide range of voltages. So as you increase the voltage, you increase the current, and over the range they show here. Now, here's part of this graph that doesn't make any sense. What do they mean by negative voltage and negative current? That makes no sense. They should start at 0 and go up. They shouldn't have this line going down here. It's just sort of sloppy graphics on it. Okay? Resistance is constant over a wide range of voltages. The relationship between the current and voltage is linear for the ranges we're looking at. The slope is related to, in fact, it's 1 over the resistance. Now that's because they put the voltage on the horizontal axis, which, by the way, is usually the independent variable. That's why they put it horizontal. Current being vertical, but because voltage is equal to IR, you had to do voltage times 1 over R to get I. So that's why the slope is 1 over R rather than R. But it's related, directly related to the resistance. Okay. A non-ohmic material would be one whose resistance changes with the voltage or current. The voltage-current relationship is not linear, but in this case looks to be curvilinear or something. A diode is a common example of a non-ohmic device. Now, its curve will not look just like this. It's usually more of a step function type thing, not nearly so smooth as this. Okay. Sorry if I have to pause every now and then, like I was telling the ones who were here earlier. I got to eat only a salad today and haven't had a chance to eat any rest of my lunch. And it's been a long time since breakfast. So anyway, this would be an example of a non-ohmic material. It would have current depending on voltage in a nonlinear sense. All right. Before we hit resistivity, let's do a couple, I think they'll be pretty quick quizzes. In 17.9a, this one, does the resistance of the, oh, I'm sorry. They've got the wording badly here. It says, does the resistance of the diode increase or decrease as the positive voltage increases? Well, that is 17.9b. That one. Okay? So it's wrong in the book, it's wrong on the slide set. So in 17, oh no, it said it right, I'm sorry. In 17.9b, does the resistance of the diode increase or decrease as the positive voltage increases? What would you say? Does the resistance of the diode increase or decrease as the positive voltage increases? What say you? That figure, this diode, they claim, does the resistance increase or decrease as the voltage increases? Second? Okay, the slope increases, but if you recall from the previous slide, the slope is 1 over the resistance. So if the slope is increasing, then the resistance must be decreasing. So that should be B. 17.4 should be B. Let's see what they say. 17.4, sure enough, is B. Okay, 17.5. All electrical devices are required to have identifying plates that specify their electrical characteristics. The plate on a certain steam iron states that the iron carries a current of 6 amps. So let me get my pen activated so I can write here. So I is equal to 6.00 amps when connected to a source of 120 volts. They write it as 1.20 times 10 to the second. Let's just say the voltage, or delta V, is equal to 120 volts. Now I'm going to put a bar over that zero, meaning that zero is significant. Okay? What is the resistance of the steam iron? Can you tell me? Can anyone tell me what Ohm's law says? Now can anyone tell me what Ohm's law says? IR. I being current. Okay? So, let's go back here. And we said delta V is equal to IR. What we're looking for is the resistance. Okay? So let's solve that equation for R. Solve for R. Say again? Not quite. Do it. R is equal to delta V over I. Now, are y'all familiar with Ohm's law enough to do this easily back and forth? Probably not. Okay. All you have to do is divide both sides of the equation by I. And the i's go out here. R is equal to delta V over I. So there's another way to express that same one. And we can express the sounds here also. We're on page 573, quick quiz 17.5. Okay? Can you write one other form of Ohm's law? There's one. Delta V is equal to IR. We wrote it as R is equal to delta V over I. What's one other way we could do it? I is equal to delta V divided by R. There's a third way. Now, I don't know if y'all are familiar with this or not, but when I was in the Navy, of course, I knew all of the stuff. I'd already had, my college training and stuff. Was in physics, so I didn't have any problem. But when they were teaching in the naval classes, they did this. Now, some people like the circles, and some people like triangles. I tend to prefer the triangles, but it doesn't matter. And when you have something like Ohm's law, and there's lots of different things that will fit the same pattern, the one that is equal to the product of the other two, put on top, delta V, or delta V. And then put the other two down here, I and R, I and R. Now, the horizontal line is a dividing line, just like we use it otherwise. The vertical line, let's put the times in, that's the multiplication line. So delta V is equal to I times R. That was the first illustration. The one we did last was I is equal to delta V over R. And the one we just did, was R is equal to delta V over I. So if you like using this mnemonic device, you don't have to sit and divide by stuff like this, as long as you get them in the right order. Okay? And that's usually pretty easy to do. If they first gave it to you in this form, then whatever's on top goes on top, and whatever's on bottom goes at one of these two bottoms, and the other one goes at the other. So you can always set them up this way. And you'll find lots and lots and lots of applications for this kind of procedure. Okay? Now, that was a little quickie. So let's solve for R. That's equal delta V, which we found to be, they gave us as 120 volts. I was 6.00 amps. And if you divide this, 6 will go into 12 twice and carry up your 2. That would be 20 ohms. I can't write, but that's the concept here. 20, yuck. Okay, 20 ohms. Okay, let's see how they did on their multiple choice. They said 0.0500 ohms, 20.0 ohms. I didn't put my 0.0 down. We had 3 significant digits everywhere, so I should have put a 0.0. Or 36.0 ohms. And of course, we agree it's, or don't we? 20. Not 2, but 20. And this was 17.5. B is 20. Good for them. Any questions on that? At all? Okay. Now let's look at a slightly different concept that's related to it, and that's the resistivity of a material. The resistance of an ohmic conductor is proportional to its length, L, inversely proportional to the cross-sectional area, A, and the constant proportionality then is its resistivity. And that symbol, by the way, is rho. That's not a P. Okay? Now, you can think of this kind of similar to water through a hose. Okay? If you have a very, very, very long hose, is your pressure going to be greater than if you had a very short hose? No, it's going to be less, because the resistance of the hose for all the length of that hose is just more and more, and that's going to cut down and increase your resistance to the water flow. So it's directly proportional to the length, but inversely proportional to the area. Because if you had a very small hose, very small diameter, it's going to take a lot of pressure to get it to go through there, because the surface area is really close. But if you have a great big hose like this, then lots of water can go through. It's only on the surface, on the edges, that you meet a lot of resistance. So a lot of water can go through the middle without ever feeling much resistance from the middle. So it's inversely proportional to the area. By the way, wouldn't that be a reason firemen use hoses that are about this big rather than a garden hose. They just aren't going to get much water on the fire with a very little hose. So resistivity rho is the constant proportionality and is called the resistivity of the material. It says see table 17.1. And let's see if we can find that. Here we go. This lists some of the resistivities of materials. So here's the other deal, folks. Okay? Resistance varies with length, cross-sectional area, and stuff. Resistivity of a certain material is always going to be constant. It's a characteristic of the material. So that's why we would ever want to use resistance fits Ohm's law like a glove. We don't usually want that, but if we do want to compare it to other materials, we want to look at resistivity. And I don't know if you remember from your from your thermal chapters that you had in 201, but you haven't had them yet because you're in 201. We haven't gotten there yet. But the thermal resistances look an awful lot like these electrical resistances or resistivities. The very lowest is silver, 1.59 times 10 to the minus 8 ohm meters. Okay? Now, wait a minute. If that has the lowest resistivity, why do we use copper in the wire rather than silver? Anyone have an idea? If silver has a lower resistivity, then you'd have less line loss. Why don't we use silver rather than copper? Ah, it's way more expensive. That's the primary reason, but yet there's another reason. What can I do with this? Bend it. Silver is much more, let me put it the other way. Copper is much more ductile, there's other words for it, than silver. Silver is pretty brittle, so that wouldn't make very good wires anyway. And the other thing is copper isn't far behind. Silver is 1.59 times 10 to the minus 8. Copper is 1.7. So there's not a lot of difference. 0.11 or 0.11. No, 0.11. Not very great. The next best conductor or lowest resistor is gold. Okay? 2.44 times 10 to the minus 8. So you see the jump between silver and copper is much less than the jump between copper and gold, which is the next best, lowest resistivity. Then from gold to the next one is aluminum, 2.82 times 10 to the minus 8. So aluminum's not a lot better than gold. I mean, gold is a little bit better than aluminum, but not by a huge amount. Actually more than the difference between silver and copper. Those are really, really close. And then another one, and now I'm not saying these are all the metals, but another one is tungsten, which is almost twice the resistivity of aluminum. So it's several times the resistivity of copper and silver and the others. Okay? Now, does anyone know one use for tungsten? At least it used to be used for this. They may have come up with some better. The filament in an incandescent light bulb used to be tungsten. Again, they may have come up with some materials that last a little bit longer or whatever, but that's the deal there. Now let's go back to this resistance model. Okay? So if you think about that filament in the light bulb, think about some characteristics of it. Number one, it has a pretty high resistivity, so it's going to get hot and give off light sooner than something that had lower resistivity. The other thing that increases the resistance, have you ever really carefully looked at the filaments in the light bulb, especially some of those clear bulbs that that you can see the filaments really clearly. If you'll notice, they're little springs looking things, coils like that. What does doing as a coil like that do? It increases their length. The greater the length, the greater the resistance, right? And the other thing, have you noticed how fine they are? They're about like, I don't have many, but a hair fiber, okay? Really, really thin. So a very small area, meaning a large resistance. So those are all three features are illustrated in the filament of a light bulb. High resistivity, long length, and very, very tiny surface area. Does that make sense? Okay, after tungsten, iron, it's pretty high resistivity. Platinum, just a little bit higher. Lead, higher still, in fact, twice what platinum is. Nichrome, have you ever heard of nichrome? Have you ever heard of Shakina? She's here, okay. And I forgot to mark the people absent that didn't come to lab in the last class. Okay. Anyone ever hear of nichrome? Have you ever seen nichrome? Used nichrome? By the way, my guess on nichrome, that's an alloy of nickel and chromium. I can't swear to that because I haven't seen how they manufactured it. The name sure sounds like it. It's not a good conductor, has a high resistivity. 150 times 10 to the minus 8. You've all touched nichrome, I bet. You know the heating elements in if you got electric range, the thing that turns red when you turn it on, or the oven, if you have an electric oven, that thing that goes around there that turns red when you turn it on, nichrome. Heating element. If you ever have a space heater, the space heater have those little coils that turn red when you turn it on, most of the time that's nichrome. Very large resistivity, meaning it's resisting the current, which produces a lot of heat. Carbon, pretty high resistivity, 3.5 times 10 to the minus 5. Germanium, even higher, 0.46. Silicon, 640. Okay, the others are 10 to the minus 8. This is 10 to the positive 2. Glass can vary from 10 to the 10th to 10 to the 14th, way up there. Hard rubber, 10 to the 13th. Okay? Hint. Hard rubber, what you reckon this is? If it's not rubber, it's a material like rubber. Why do we want that to have a high resistivity? So we won't get shocked. Yeah, if that is will allow current through, then we're going to get shocked like crazy, and you'll start fires. It'll be just bad all the way around. Sulfur, even higher, 10 to the 15th. And fused quartz, 75 times 10 to the 16th. Now, I'm not absolutely certain what fused quartz is and what it's used for, but let me just give you some examples of something that's pretty close to it. Have you ever seen on power poles those ceramic-looking devices that hold the wires off the wood? That is probably, if it's not fused quartz, it's probably something very similar. Very high resistivity, so you don't have any conduction to it. Okay? They also list here the temperature coefficient of resistivity, which indicates all these are pretty small numbers, which means there's not a lot of increase over temperatures. Okay. There's a nice little blurb here on the dimming of aging light bulbs. And I'll let you read that. I don't think they go in. Let me just see. No, they don't. So we'll, I'll just let you read it. But I will mention this one. Okay? There is always a little bit of temperature variation with resistivity. Not a lot, but some. Okay? That's what they talked about here. Oh, there we have it. Temperature variation of resistivity. I didn't realize we were on that slide yet. Oh, we're not. We'll get to that later then. Before we do that, let's do quick quiz 17.6. Suppose an electrical wire is replaced with one having linear dimensions doubled. So you've doubled the length. But also the radius doubled the radius as well. Does the wire now have more resistance, less resistance, or the same resistance as before? So you doubled the length and doubled the radius. So this have more resistance, less resistance, or the same resistance. What's that?
Is it double? No, it's not. Okay, so
Just
same.
more or less the same.
The same.
Okay.
Is less?
Okay, let's take a look and see. Okay, let's say this R is the resistance of the first wire. Okay, the second resistance, this will be R1, R2 is going to be rho. That doesn't change. It's the same material, so that doesn't change. But we now said 2L, twice the length. But before we deal with area, we have to come over here. The second area is pi times 2R squared. Whereas this one is pi, A1 is pi times R squared. Right? R1 squared. This is R, no, just R squared. Okay. Because we're doubling it, actually. Okay. Pi R squared, and this is pi times 2R squared. Okay? Now, what does this give you? The second area is pi times 2 squared, which is 4 times R squared, so that's 4 pi R squared. So when you do the second area down here, it's 4 pi R squared, where the R's are the same, the L's are the same. So this one is, let me rewrite this. R1 is equal to rho L over pi R squared. And this is 2L 4 pi R squared. Okay? So when you divide that out, your R2 is equal to rho L over 2 pi R squared. So that is exactly half of the resistance of this one. So it's actually less. Because you see, when you double the length, yeah, that gives you more resistance, but when you double the area, it gives you doubling the, not doubling the area, doubling the radius quadruples the area because of the R squared relationship. So that actually gives you less resistance, half the resistance of before. So which one was that? That was less resistance. 17.6 should be B. Let's see what it is. 17.6, sure enough, is B. All right. Now we move to temperature variation of resistivity. For most metals, the resistivity increases with increasing temperature, meaning the resistance increases with increasing temperature. With a higher temperature, the metal's constituent atoms vibrate with increasing amplitude, and therefore they will offer more resistance, more resistivity. The electrons find it more difficult to pass through the atoms because the atoms are vibrating with increasing amplitude, so when there are collisions, there are stronger collisions, they get bounced back more. So you have more of that tortuous movement. Okay? For most metals, the resistivity increases approximately linear with the temperature over a limited temperature range. And this is the formula for this. This is resistivity now. And that would be your base resistivity, that's some reference temperature T0, usually taken to be 20 degrees Celsius. Someone tell me what 20 degrees Celsius is, approximately. Hot, cold, warm, cool. Second? It's what?
Are you asking how it feels? What are you asking?
You may have been on it. What did you say?
No, I just said it's like room temperature.
It's room temperature exactly, or very close to it. Right now we're sitting, they say, at 71 degrees. 20 degrees Celsius would be 68 degrees Fahrenheit, right around room temperature. So that's what they usually choose to be the reference temperature. Then the alpha that you see here, that's your coefficient of resistivity, okay, depending on temperature, okay? It's a fairly complicated looking formula, but it's really not too bad. Because if your actual temperature is room temperature, or whatever you choose that T0 to be, this is 0, then you're adding nothing to here, 1 times this, that is your rho 0, okay? And as you increase this temperature, this resistivity goes up ever so slightly, okay? Decrease that temperature, the resistivity decreases ever so slightly. But it's linear in that it reacts to that. And if you remember the table that we had, those were the alphas in that table. Let's go back. No, they weren't here. It was in the book. If you go to that table on page 574, the temperature coefficients of resistivity, those are your alphas. They're all fairly small numbers. Now the bizarre thing is carbon, germanium, and silicon all they go in the opposite direction. You increase temperature, it decreases the resistivity. Decrease temperature increases the resistivity. Bizarre, but true. And by the way, those are, still fairly small numbers. Okay. Oh, here's the formula. I thought we gave it on the last slide. No. Oh, we already did this. Yeah. All right. That was all 17.5. Okay. Let's move on to electrical energy in a circuit, 17.6. In the new edition, it's electrical energy and power. Okay? In a circuit, as charge moves through the battery, the electrical potential energy of the system is increased by delta Q, delta V. Okay? The potential energy increases by that amount. Now that should make sense, right? Because what is voltage? Voltage is energy per charge, so therefore energy would be charge times voltage difference. And that's exactly what you got here. The chemical potential energy of the battery decreases by the same amount. So the electrical potential energy increases, chemical potential energy decreases. As the charge moves through a resistor, it loses that potential energy during collisions with atoms in the resistor. Okay? Especially if that was nichrome as a heating element, it's going to lose them big time. Okay? The temperature of the resistor will increase. Always. Okay? The temperature of a resistor as you've got current moving through it tends to increase. How is energy transferred in the circuit? And this is the figure 1711 in your text. Okay? Consider this circuit here. What we have, now this is kind of a strange way to draw this, but it's okay. This shows a battery, right? Or some sort of power supply going from minus to plus, and we're going to assume the current flows in the direction that a positive charge would flow if you had positive charges flowing, okay? Positive current travels clockwise from positive to negative. I don't know if I would say clockwise. It travels from positive to negative, okay? Now, over here you've got a resistor, okay? Now, if this wire is a great conductor, in other words, not losing much energy at all, then the voltage difference between A and B will be exactly the same as the voltage drop. Here it's an increase going from A to B. Here it's a decrease going from C to D. Because B is at the same level as C, A is the same level as D, so if this is increasing going this way, it's decreasing going that way with the current. Now the thing that I found sort of strange about this is they drew a ground here. It's okay, especially if you had alternating current. You always count on it going to ground. With a DC current, we usually just count the negative pole of the battery as being ground. But they drew them both in this way. Imagine the quantity of positive charge, delta Q, that moves around the circuit from point A back to point A. Guess what? You do not lose any charge. When the current goes through a resistor, it does not lose charge. It loses energy on those charges. The charges are conserved. You cannot create nor you cannot destroy charge. It's there. It's always there. A few exceptions, but nothing we're going to be doing here. You do not create or destroy charge. Charge is conserved, so it's the energy that's changing as you go. So when you go around the loop, you first increase the energy on those charges. Then through the wire, you assume there's no energy change. When you get to C, it's the same as the energy you had at B. When it passes through the resistor, that's when it loses its energy to get to D and go back to A with no loss. Okay? Does that make sense? Is anyone listening? Okay. Now, point A was called the reference point, and the symbol there for grounding said that there at ground the potential is taken to be 0. As the charge moves through the battery from A to B, the potential increases by your delta Q delta V, which is the energy increases, and that's the energy you've given to those charges. The chemical energy in the battery decreases by the same amount. It's the same thing they said on the earlier slide, like right back here, okay? So they're just repeating what they said there. All right. As the charge moves through the resistor, though, from C to D, it loses energy in the collisions with the atoms of the resistor. The energy is transferred to internal energy of the resistor, and when the charge returns to A, the net result is that some chemical energy in the battery has been delivered to the resistor, caused the temperature to rise, heated the surrounding air, whatever it was doing, and there's where the energy is lost. Not created, not destroyed, just dissipated. Okay? Does that make sense? Now here are the formulas we're using with that. The rate at which the energy is lost is the power. Change of energy is per unit time is power. So the energy was delta Q delta V. Take the time rate of change of that, in other words, divide by delta T. But the voltages are changing with time. The charge is delta Q delta T is I, the current, the rate which charge is moving. The voltage isn't moving, it's just there. The charge is moving, so the delta Q for delta T is I. So here we have another formula. P is equal to IV, or I delta V. That's power. Okay? Now, that formula works just as well in your triangle or circle as the other did, as Ohm's law did. You can either draw your circle or draw your triangle. I sort of prefer triangles, but I don't really use them that much anyway. I'll just know the formula. And you put P, I, delta V, P, I, delta V. It looks a lot like Ohm's law, and then if you wanted to know current, that's power divided by voltage. If you wanted to know voltage, that's current divided by time. And I'm trying to wreck my power cable here because I was using it to show something and got it under my wheel. Okay, so there's an equation for power in terms of current and voltage. By the way, this is used all the time by your power company, your electrical supplier. The voltage that comes into your house is typically somewhere around 360 volts, 240 volts. Most of the outlets that you have are around 120 volts. Okay? However, at that low voltage, you tend to have high currents, and therefore you have high energy loss. Okay? So what power companies do, they raise the voltage big time, dropping the current big time, minimizing the line loss, which minimizes the heating of the lines. Okay? So there's other ways that we can look at this, and here's a couple of them. Someone tell me what Ohm's law says. Delta V equal IR. Very good. Okay? So therefore, in this formula, what we're going to do is put IR instead of delta V. So that gives you I squared R. And there's another example of a power formula, a power law formula. This is the one that we use when we're dealing with voltages and currents. This is the one we use when we're dealing with currents and resistors. Okay? And the power that's lost when you have high current is really big time. When do you have high current? When you have a lot of heat produced. So think about this. Your space heaters, your air conditioning system, your clothes dryers, your ovens and your ranges, anything that produces a lot of heat, there goes your power consumption. Big time. Sometime think about this. If you got some time to kill, you know where your electrical meter is? Okay? I know the one, we have a place over in Georgia, and I know that meter is real close to the air conditioning. And what you really, I don't usually have time to stand around and watch this, but in the summertime when that's going to be coming on and going off a bit, go over and look at the wheel turning. If you got one of those that you can see the wheel turning. See the wheel turning, and then when the air conditioner comes on, you will see it go up. You will see that thing speed up. Or, if you know somebody inside is going to be turning on the clothes dryer, then say, wait a minute, let me go outside and look, and you watch that wheel, and when that clothes dryer comes on, And our place over in Georgia, the vent is just right there too. I can tell when it's coming on. Watch that speed up. You can do the same with the electric range. You have electric oven and range there. Just have someone inside, wait a minute, and turn on the oven, turn on the range. Watch that range speed up. Okay? Anything that uses a lot of current, which means it produces a lot of heat, you're going to be using lots of power. The rate of power is great. But let's do something else with this. Let's use remember we also said that I, in Ohm's law, was equal to delta V over R, right? Everybody agree with that? Okay, so this time we'll take our same formula here, okay, but this time we will replace the I with delta V over R. Delta V over R, multiply that by delta V, and you get delta V squared over R. Okay, and that's your third representation for power. Power is equal to IV, power is equal to I squared R, or power is equal to delta V squared R. Okay, which means if you increase your voltage big time, or decrease your resistance big time, but the voltage has a higher potential for change, that's going to also increase your power consumption. Make sense? Okay. Now, what's the SI unit for power? What? 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 All right, okay, never mind. Okay. It's the watt. Okay? Now, for that to work, I must be in amperes, R in ohms, and delta V in volts. Now, I found this a little strange the way they wrote it. If they're going to capitalize the ampere and capitalize the volts, why aren't they capitalizing ohms? They're all three named after people, so I found it strange they did it that way. Okay? The unit of energy is usually, now, power is watts, but the unit of energy in electrical companies is not the joule. A lot of times we say, and it is, the SI unit for energy is joule. However, for electrical energy, and here's the reason it's on the board right now, they typically use kilowatt hours. And here's why. We just said power is equal to energy over time, right? So another way you could refer to energy is equal to power times time. There's another example of using that formula. And if you did that, okay, then your power measured in watts and your time measured in hour, but make that kilowatts, that makes your energy unit a very big unit. Okay? Kilowatt hours is a lot of power over a long period of time. In fact, this is defined in terms of the unit of power and the amount of time supplied. 1 kilowatt hour is 3.6 million joules. Okay? Now remember we said before, back in 201, a joule is a fairly small amount of energy. Okay? But just imagine your energy bills if they came to you and they had how many millions of joules you had used. You say, oh my goodness, look at that number. I've used millions and millions of joules. I need to cut back. Whereas if they use a large unit like this, and maybe you've only used 120, 450 or something like that kilowatt hours, you say, oh, that's not too bad. But if it had hundreds of millions of joules on there, you would have said, no, I'm really wasting energy, just because the number would be so big. So I think that's why the power company doesn't use joules, they use kilowatt hours. Both of them are legitimate units for energy. One of them is just not SI, okay? It's related to SI, but it's not. All right, that was, oh, whoa. Quick quiz 17.7. A voltage delta V is applied across the ends of a nichrome heater, okay, wire, having a cross-sectional area A and a length L. The same voltage is applied across the ends of a second nichrome wire, having a cross-sectional area A and a length 2L. Which wire gets hotter? The short wire or the long wire? Or more information is needed. A is the short wire, B is the longer wire, and C says more information is needed. What you think? I'll get there one of these days. Basically, these formulas here. Okay. The resistance of that wire, the road is the same. They're both nichrome, right? The size of the wire is the same. The areas are the same. All you've done is increase double the length, right? What does that do to your resistance? Double the length, double the resistance. And therefore, your, what was the question? Which wire gets hotter? Double the resistance? That wire gets hotter. So that would be the longer wire, B. Okay? 7, wait a minute. I think they got this wrong. Voltage applied across the ends of nichrome heater wire having cross-sectional area A and length L. The same voltage applied to the ends of the second nichrome heater wire having cross-sectional area A, length 2L. Which wire gets hotter? They say the shorter wire does. No way. The longer wire does. Okay? Because the resistance increases. Now, let's back off and look at it from a different angle, though. Let's look at it from this angle. The resistance increases by Ohm's law, then the current would decrease, and I guess by that it would say that the current decrease is stronger than the resistance increase, and therefore it would get less. I don't know. I still don't buy it. Okay? Let's look at 17.8. For the two resistors shown in the figure, do any of you have your books tonight? You do. Most of you don't. So let me, whoa, wait. All right, let me try to draw these two figures. For the two resistors in this figure, rank the currents. Okay. Here's the figure. Here's your voltage source, delta V. Okay. This is point A, point B, point C, point D, point E, and point F. Okay? For the two resistors shown in this figure, and by the way, this is really bizarre. Oh, I got what they're saying. This is a 60-watt bulb, and this is a 30-watt bulb. Most of the time with resistors, you don't list it as watts. You list it as ohms. But if you're talking about light bulbs, then that would be okay. Okay? For the two resistors shown here, rank the currents at point A through F from largest to smallest. Okay? Rank the currents for A through F, largest to smallest. Which is the largest current, you think? Where do you have the greatest current flow?
D.
Second?
D.
D? This one right up here? Second? Wrong. Okay, what is right?
Yeah, that's right.
Oh, I don't know. It's not quiet. It's called Anna? B?
B.
Yeah,
Okay?
that's wrong too.
Okay. Now, that's half of it.
No,
A.
it's
A and B are the same.
Oh.
All right. A and B are the same. So I sub and instead of from greatest to smallest, is that right? Rank the currents from A through F from largest to smallest. So I sub A is equal to I sub B. Guess what? Current can't be created nor destroyed. So whatever is going into A has to be coming into B. Got to be the same. Now, at this point and that point, the current splits. Some current goes here and some current goes here. Right? So therefore, these two currents have to be, these two and these two have to be less than these because these, they add back together coming in. So that's why A and B have to be the greatest. All right. Now, usually we don't think of it in terms of resistors in terms of wattage, except for light bulbs. Now, what does it mean for a 60-watt bulb? Is that going to have more current or less current than the 30-watt bulb? Okay? If those were ohms, I would say you're absolutely right. But these are watts. Because guess what? Guess what? The same voltage here is there and is there. Okay? And power, that's what the watt measures, is voltage times amps. Same voltage, greater power, greater current. So C and D are next. This is greater than I sub C, which is equal to I sub D, and that is greater than I sub E, which is equal to I sub F. Because you don't lose current, you lose energy going across the resistor, you don't lose current. Same current going in has to be the same coming out. So therefore, that's how I would order these. So there, A was A equal IB, good so far. Greater than IE equal IF, wrong. Well, it's greater than, but that's not greater than IC equal ID. B was IA equal IB, right. Greater than IC equal ID, right. Greater than IE equal IF. B, bing, bang, okay. And then C, totally wrong. IE equal IF, that's right, but that can't be greater than any of the others because it's lesser than the others. So 17.8 had better be B. Will it be B? Let's see if it is B. 17.8, sure enough, is B. Good for them. They got that one right. 17.9. Two resistors A and B are connected in a series circuit with a battery. The resistance of A is twice that of B. Which resistor dissipates more power? Okay. Let me draw this for you. I'm going to go on and delete what's here. Is that all right? Okay. So let's draw 17.9. Two resistors connected in series with a battery. So let's put the battery here, one resistor here, and one resistor here, and back to the battery. Okay. Forget about the squiggly lines. Okay. This is resistor A. This is resistor B. In series with the battery. The resistance of A is twice that of B. So if this is R sub B, this is 2 R sub B. Twice the resistance of B. Which resistor dissipates more power? Resistor A, resistor B, or more information is needed? What do you think? Okay. All right, let's think through it and see. Number one, in a series circuit, the current is always the same, right? So this I that's going through here is going through everywhere. So the current here is I. Same here, I. Same here, I. Same current everywhere in the circuit because it's a series circuit. Okay? This voltage here, we'll call it delta V. We don't know what it is, but that's what it is, delta V. Now, the question is, which resistor dissipates more power? Okay? Now the I's are the same through both of them. Okay? The resistance here is greater than that. So which dissipates more power? If you turn back here, this gives us I's and R. Yeah, I's and R. So the power through A would be I squared times 2 RB, and the power through B would be I squared times RB. So that would indicate the power dissipated through A should be twice that dissipated through B. However, I want to hold forth something just in case. Okay, 17.9 says A. And what was A? Resistor A. Okay, sure. Okay. Number 10. The diameter of wire A is greater than the diameter of wire B, but their lengths and resistivities are identical. For a given voltage difference across the ends, what is the relationship between PA and PB, the dissipated power for wires A and B, respectively? So let me go back to this one, clear this off the screen. Okay, 1710. Diameter of wire A is greater than the diameter of wire B. Okay? But their lengths are the same. Those are the same. And the resistivities are the same. Okay? For a given voltage difference across the ends, so the delta V is the same here as here. Okay? For the given voltage, a given voltage difference across the ends, what is the relationship between the power PA and PB, PA, PB, for wires A and B, respectively? So let's go back to our power equations. Here they are. I think I'm going to erase this because it's pretty messy. Okay? Now, what was different there? We knew it was the same voltage on both of them. All that we know is that resistance changed. Okay? And since we know it's the same voltage across them, let's use this one. Okay? Now, the resistance of A was less than the resistance of B because it had a larger diameter. So if the resistance of A is greater, that means the power through A would be, the resistance in A is less, that means the power in A through A is greater. Now that seems counterproductive, counterintuitive, but it is. Okay? So what we're saying is that, that's what we're looking for. That P sub A is greater than P sub B. Okay? So that should be C. 1710, we think, is C, and sure enough it is. All right? Now let's look quickly at superconductors. There is a class of materials and compounds whose resistances fall to virtually zero between some constant temperature, some certain temperature. Now that would be the critical temperature. It may differ for different materials and different compounds. So it's not all the same T sub C. But past some temperature for these superconductors, the resistance basically goes to zero. The graph is the same as normal metal above T sub C, linear ohmic material here. Now, for different materials, that can be very high or very low. I mean, whatever. It could be anything. But then when you get to the critical temperature, which is this one down here, between here and here, it's non-ohmic. Okay? Actually, it's almost ohmic there, but a different slope here. But below this, it falls almost to zero. Now, look at those temperatures, though. Okay? 4K, 4.2K, 4.4K. Those are really cold. Remember, you can't get below 0K. Theoretically, it cannot happen. You cannot get colder than absolute zero. So you're down awfully close to as cold as you can possibly get. room temperature be measured in K? Anyone know? What's the relationship between Celsius and Kelvin? Say again? That's Celsius and Fahrenheit.
And it's plus 200 and like something.
Say again?
And it's Celsius like plus 200 and something.
Yes, about 273, I believe it is. So normal room temperature would be 293. Okay? You're down here at 4. Okay? Just imagine how cold. Freezing point of water would be 273. You're at 4. Okay? 4K. That is incredibly, incredibly cold. Now, some of them are not quite that low, but they're all pretty low. Okay?
It's 7 o'clock.
The what?
It's 7 o'clock.
It's 7 o'clock? Okay. We only have just a couple pages, so I'll try to get through this in a hurry then. Okay? The value of TCC is sensitive to chemical composition, pressure, crystalline structure. Once the current is set up in a superconductor, it persists without any applied voltage since the resistance is 0. It doesn't ever lose its current. It just keeps on going. Even though you're supplying no more voltage to it, it keeps going and going. Energizer bunny. Here are some of the superconductor timelines. It was first discovered by, I don't know how to pronounce his second name, H. Hemmerling Hannes, I think is how you say it. That's in 1911. But almost nothing was done for another 75 years. Well, I'm sorry, that's not quite true. A higher temperature conductivity was discovered by Bednorz and Müller. Now, Müller sounds like a German name. I don't know what Bednorz is. Hannes sounds like Dutch or something. Superconductor near 30K. That first one was down here at near 4. Okay, this is way warm. I mean, still really cold. 30K. 1987, that didn't last too long. Went up to 96K and 105K. Fantastic. Currently, okay, just made it in the class. So we're only missing Brianna tonight. We now have some superconductivity up around 150K. Okay. There are more materials, more applications. They are finding more all the time. Now, this whole concept of superconductivity, if I'm not mistaken, I think at least 4 Nobel Prizes have been won by people studying superconductivity. It's a very, very promising field because there's some really neat stuff you can do. If we can just get it at warmer temperatures so it doesn't, the energy you save by having superconductivity, you don't use up by getting it cold enough to keep superconducting. Okay, that's the problem. Okay, you have a table in the book that gives the critical temperature for various superconductors: zinc, aluminum, tin, mercury, lead, niobium or something like that. Niobium stanate or something, no, stanide, I think it was how you say that. Niobium germide or something like that. Then they really get complicated. Yttrium, barium, copper, and oxygen. Bismuth, strontium, calcium, copper, and oxygen. Tellurium, barium, calcium, copper, oxygen, and mercury, barium, calcium, copper, oxygen. Okay, that only gets us up to 134, so we're somewhere in between 87 and current with those. Those are the critical temperatures. Okay. think that's all for that. Oh, here's the last one. A good conductor does not necessarily, and that's what I was going to say. Going through that thing there, that list, did you see silver anywhere in that list? No. That was your best conductor at normal temperatures, doesn't make a good superconductor. Did you see copper anywhere in that list? Well, in some of the compounds later on, but not after your copper, gold, didn't see any gold in that list at all. Aluminum, which is not a great conductor, can be a superconductor at very cold temperatures, but it can be. Some of the things that weren't very good conductors, go back to that list about your resistivities. Germanium, way down there, and yet it makes a really good superconductors, or at least one of them has a really good superconductor. Carbon wasn't anywhere in the list. Nichrome. Lead was up there, it makes a good superconductor. A lot of the others aren't even on the list. Okay, so it's really bizarre. No correlation between conductivity at normal temperatures and conductivity at very cold temperatures. Okay, so good conductors do not necessarily exhibit superconductivity. One application is the construction of superconducting magnets. Now, I can easily imagine this is frost on that magnet because it's at very, very low temperature. And if you get a current moving, you got a magnetic field. Moving current produces a magnetic field. This is suspending that in air. Okay? And again, you get some frost buildup on it, but it's still suspended. This is all frost buildup on it because it's so terribly cold. Can anyone think of an application of this? Have you ever heard of the super train they have in Japan? I can't think of the name of it. They have an extraordinarily fast train in Japan. How do they make it go so fast? They basically run it on the track with a magnetic field through a superconductor. It elevates the train off the track so you have absolutely no friction between the wheels of the track. In fact, it doesn't have wheels. You use air pressure and blow, I think that's what they use, blow it down, or maybe a rocket or something. I don't know, but there's no loss due to friction because they keep it super cold, elevated off the track. That's an application. All right, electroreactivity of the heart. Let's not beat this to death. Are any of you in medical type fields? Oh, you are. Okay. Every action involving the body's muscles is initiated by electrical activity. Later we'll talk about the reason for that. Basically, the potential difference between sodium and potassium ions. That's what sends the signals. Voltage pulses cause the heart to beat. Your brain is sending out that message every second or whatever it is to telling the heart to beat. Actually, the heart beats in a rhythm because certain valves open and close and stuff. So, yeah. The voltage pulses are large enough to be detected by equipment attached to the skin. Guess what we're going toward here? Electrocardiogram. That measures those pulses. So the operation of the heart, the sinoatrial node initiates the heartbeat. That's where it's, oh, there it is, SA. Okay, that initiates the heartbeat. What that does is pulls in air from pulls in blood from the lungs, I think. Yeah. Pulls in blood from the lungs. I think that's the sinoatrial node. Okay, the electrical impulses cause the right and left arterial muscles. That's it. I think they got that right. I think it's atrial muscle. I think they got that misspelled. Yeah, it's supposed to be atrial muscle. Okay, to contract. Okay, and when the impulse reaches the atrioventricle down here, okay, node, the muscles of the atrium begin to relax, and the ventricles relax, and the cycle repeats. They left something off there. The muscles of the atrial react, and the muscles of the ventricles contract, and then when the ventricles relax, and the cycle repeats again. Okay, and if I'm not mistaken, this is blood coming from the lungs into the atrium, pumped out to the body, back from the body and out to the lungs. I think that's the path we do. Okay. You can read the text and see if they go in more detail. So what an EKG is doing, electrocardiogram, EKG, this is sort of a normal. Okay. The P occurs just before, this little P happens just before the atria begin to contract. And when they do, the QRS pulse occurs when the ventricles just before they contract. That's a big muscle. That's the big muscle in the heart, the ventricles. Okay? And the T pulse occurs when the cells in the ventricles begin to recover after the contraction, and then you go through this again. So they basically are looking at this EKG. They can look at the other to see if there's any minor issues, but that's the big one. Okay? And the pulses are readable. And that's what they do. They put those electrodes around. Have you ever had an EKG? I think they put about 6 of them somewhere on your chest, and then they start reading the pulses. Now, here's an abnormal EKG, the first one. The QRS portion is wider than normal, and that indicates the possibility of an enlarged heart. Not too much you can do with that except start treating. No way really to fix it except maybe a heart transplant. Okay, that's a tough one. Okay. Another one would be abnormal EKG number 2. The time between the P pulses and the QRS pulses varies, changes. That's a possible blockage in the conduction path between the SA and the AV nodes. Okay? Go back and review what that is. That's not a very good looking situation now, but that tells them something. Now, if there's a blockage there, conduction path, there's no constant relationship between the P and the QRS pulse. This suggests a blockage of the electrical conduction path between these. This leads to inefficient heart pumping. I'm not sure, but I think that's what they call atrial fibrillation. I think that might be that one. Let's go on. Abnormal EKG number 3. The P pulses and an irregular period for the QRS pulse indicates irregular atrial and ventral contraction. So that's the fibrillation. Okay? Now, you see here it was wide, narrow, wide again, not as narrow, but right narrow. Yeah. So this is no P pulse, so you don't see the P coming in ahead of time, and an irregular spacing between the QRS pulses, symptomatic of irregular atrial contraction. That's called the fibrillation. The atrial and ventricle contractions are irregular, and this is what they sometimes call AFib. Okay. Now, what they sometimes do to remedy that is shock the heart with the paddles. You know, you've seen that clear, you know, and the body jumps, and that gets it back on a regular pattern. Okay?
Is that hurt?
I think you're out when it happens, so I don't think you sense it. But I think it probably, if you were awake, yeah, I think it would definitely have some sensation to it. Not pleasant. Okay? But usually people are out when they do that. Now, you can sometimes do an implanted cardioverter, that means it inverts, defibrillator, that's ICD, devices that can monitor, record, and logically process the heart signals, then supply different corrective signals to a heart that are not beating correctly. So you put the thing in there, and let's see, what they show here is there your ICD is there. They've implanted it here, and it runs a little wire, I guess you would say it, the lead wire there, and when it detects irregularity, it sends a pulse to correct that, sends it to the heart muscle, this is the ventricular muscle here, and makes it contract to see if you can get back on the regular play. Now, that's all they're saying here. The text may show you tell you a little bit more. The functions of the ICD is to monitor first the atrial ventricular chambers, differentiate between arrhythmias, okay, store heart signals to read out to a physician, and it's easily reprogrammed by an external magnet. Okay, that changes the thing, so you don't have to go in and do surgery to reprogram it. More functions of the ICD: perform signal analysis and comparison, what you've had to what you got now, supply repetitive pacing signals to speed up or slow down the malfunctioning heart. Now, sometimes this is called no, it's not. It's an advancement on what they used to call a pacemaker. A pacemaker fit the rhythms of the heart, made you pump it at the same time. The disadvantage of a pacemaker, what if that was set for your normal activities? Fine, but then you start walking up a hill, your heart doesn't respond because it's still stuck to the same pattern. There was a lady in our church who had one, and I can remember walking her to the parking lot, which is uphill. She said, "Sorry, I have to stop and let my pacemaker catch up." To get the blood there. Okay, so this is a little more advanced in that it resupplies. Okay, speed up or slow down the heart. Adjust the number of pacing pulses per minute to match the patient's activity. The old pacemaker didn't do that. The ICD can. That's the end of the chapter. Okay? I think we can still get the lab in. It's a pretty fine, fun lab, I think. There's a table, typical properties of the implanted cardioverter defibrillators. You can certainly read a little bit more there. And again, the questions at the end, they're all there. The most important things would be the problems, in my mind. So that's going to be closest to what your tests look like, and they start on page 586. Any of the odd numbers for any of those sections. Okay, next time we'll start with direct current circuits. So I'm going to end this, in that. If y'all want to take a quick 10-minute break, we're not much past that. I think we'll have time to get. May not take me a full 10 minutes, but it's going to take me a little while to set up. Okay, I'm going to pause. All right, I'm recording this for the others. I recorded the other. I passed out the labs, set up the circuitry as indicated on the labs while the students were reading the first page, page 193, and then following the instructions under Part A, you adjust the DC power supply And it says as instructed, and what I suggested is get as close as you can to 1 volt, 2 volts, 3 volts, 4 volts, 5 volts, and 6 volts for those 6 readings you get, and read the amps on the ammeter. Now the amps is read in milliamps, so you have to adjust that to amps, moving the decimal 3 places to the left. We started the ammeter on the 20 milliamp range, but after a while, the students found they had to go to 200 milliamp range. But then, have y'all finished taking the measurements for that? Okay. So I'm going to turn yours off for now, and we'll pick up again later. Okay? Okay. Why don't you figure it out and then I'll tell you. Okay. All right. In other words, graph your thing. What you do is graph and turn that so you can read it out from sort of hard.
So basically, these are all the
Okay. Plot. Yeah. Like it says to do. Under results, on page 194, make a graph of the 6 data points, placing the current on the horizontal axis and the voltage on the vertical axis. So you adjust it. Let me see what your numbers were approximately. Okay, 1 to 6. That's pretty straightforward. And this is going from 11 to 62. Pretty straightforward. You can do it either way you want to. It looks like maybe a little bit bigger range here. So I would say put that on the current, they said on the horizontal, so turn your page like this. And current horizontal and volts vertical. And you are going the volts 1, 2, 3, 4, 5, 6. So you see that fits perfectly. 0, 1, 2, 3, 4, 5, 6. And then you can do it horizontally. 0, 1, point 0, 0, 1, point 0, 1, point 0, 1, point 0, 2, point 0, 3, point 0, 4, point 0, 5, point 0, 6, point 0, 7. So, okay. So the students are taking measurements now, and some of them are actually at the point of drawing the graphs. And when you finish taking your measurements, let's be sure to turn things off so we say that. Unless you need to go back and check. Okay. I'm sorry? I can't hear. Did someone say something? Okay. And all of you have rulers that you can assist in the drawing of straight lines. Hence, straight lines.
Can I have one?
I delivered 2 to each table.
How do you know which one's the right resistance? Because I
What's
was
that?
calculating the resistance by putting the voltage over the current,
Okay.
and it's all different.
Okay.
Do I
That's
just?
why you graph them first.
I did.
Okay.
And then it's based on the line.
Yes. There's your graph. Do your best straight line through that.
And then what?
And then look at your.
This one is
This is your current, that's your resistance. Do a straight line, do rise over run, that gives you a slope.
And that's how I get, that's the resistance.
That's
and
your
slope.
resistance, right? Because it's voltage over
So,
current.
it's slope.
Yeah. And,
And what do we do for this page?
huh?
What do we do for this?
Okay, I'm going to give you an unknown resistor for that. But I want you to do this on the known resistor.
So the slope is the resistance.
Yes, if you do rise over run, in other words, voltage over current. So do your best estimate of the slope and see what it comes out being.
I know by our line is
Yeah, voltage is vertical, current is,
No, I'm talking about for the resistance. Is it voltage over current?
yeah. So rise over run. Yeah, but if you do your slope, see what you get. On the slope,
Oh, I didn't do the slope. I just did. Everyone's resistance.
what's that?
It's supposed to be the same for everything.
Well, you have different resistors. I mean, you got the same resistors, but you have different devices, so you may be off a little bit depending on the calibration of the devices. You should be pretty close.
How'd you get 100 in the slope? We had for our voltage 1.1, and then our current was 0.019. So if you divide the
You try your best right now.
I mean, that should work.
I do the line that it rise over run. It's 1 over 1.
I don't think so. Rise. It looks like about 6 minus 1, that would be about 5. Right on the money. And then the run looks like it's about 0.57. 0.57. Is that right?
Where are you doing that?
Rise from this point to that point. I mean, I'm trying to fit your line. Which is your best line? You got 2 or 3 of them over there. Okay, do those fit the line for everyone? Okay. Then rise to the reference of these two. The run is the difference. Work horizontal. Got it.
To get the percent error, what was the actual resistance?
Okay. The actual resistor was 100 ohms. Right on the money you got it. No. No. You're, no. Okay. Is it percent or error? Percent error. Okay. So let's first do this. What is your error? Your error is your measured minus actual. That's how much error you have, right? Okay. Positive if you measure too high, negative if you measure too low, right? So your percent error would then be your error over actual times 100. So you had a 0 there, okay? Right? Well, you measured was your actual, wasn't it? Did you tell me? No. And y'all did your slope, just got a little bit off, then it shouldn't all be awfully close.
So 100 minus 100, 12 by 100. We just
Okay, let me see. Oh, you got that?
I counted it this way, I got
50. How do you get 50?
Is
Zero to 6. I mean, 1 to 6. Okay. Okay.
I mean,
Oh,
six.
we use the.
Huh?
Okay.
Isn't your difference in y is here? 6 minus 1. 5. Exactly.
So we use these
And
values.
your run is 0.0 whatever that is. 058 minus 0.009. Okay.
Okay,
So that's not going to be.
So this is why I did that's the data. Okay, so we just use these.
What's that?
I was thinking we use like the same values for size of the run.
You use what we measured, volts over amps. And amps are in very small numbers, but they're big numbers.
Okay, so we're ready. I was basically like 5 and 0.049.
5 divided by 1, is that right?
Yeah. So 5 divided by 0.049.
106.
So that's our.
No, the actual is 100. So you're 2% up. Okay. Anything less than 15 is good. Basically, 102 is not the best you can do.
We're ready to do the second one.
Okay?
We made that a little bit harder.
Yeah, definitely.
Alright, you
You
know,
try to do the most difficult way. Yes.
Okay, that's my job, is to make it hard. Yours is to make it easy. Now, you might need to. Huh? I'd say start back where you did before. 20. See what you get. If it goes off scale, then adjust accordingly. So back
yeah,
again.
but it's on this.
Okay, well, let's see if we.
Okay, so now we're gonna do the second
0,
round.
0, 2, 6, 7.
We're ready to do the second round.
Okay.
So this is an.
No,
So the other one is unknown.
no,
They're both unknown.
Well,
So
I
how
thought
do we
you
do
were
this one?
saying that,
Okay.
but you'll probably have different
So
amp
do
readings.
do this point minus this.
Well, so the
What did
question-
you set yours on? Oh my god, it went down both ways. You said it was that thing?
Yeah, you want to go up.
Okay.
Y'all okay?
Probably.
All right, if there are no more questions right now, most teams have done their first, and a couple teams are starting on their second. So I'm going to pause this for now.